Today we will talk about the characteristic of vectors. First, we will talk about what's a scalar quantity, which is the numbers we usually use is just a number, like a regular number with no direction. So for example, if I talk about 4 kilogram, that's a scalar quantity. Or if I talk about $3, there's no direction to those numbers. But when we talk about vector quantity, it is defined by a number and also a direction. So for example, if I'm talking about vector AB, I'm gonna start at A, finish at B. So this is vector AB. And there's gonna be a number, so a length. Let's say this is 5 kilometers per hour. And we're gonna need also a direction. So to check the direction, we go from horizontal, and let's say we measure, that would be 40 degrees. When you look at your vector, you always have a head, this is where it's going, and a tail, this is where it's coming from. We can also identify a vector with only one letter, for example, vector v, that would be, let's say, 3 meters per second. And to check the direction of this vector, we need to find the horizontal, and our angle would be like this. Now, when we have the length of the vector, we call this the magnitude. So that will be the number that describes the vector. So number that describes the vector. Sometimes we will also call it the norm. You will see it also, it's the same, the norm of a vector. And the way to write it down is to use two lines like this. So this means the norm of vector v could be, for example, 3 kilometers. It means how long it is going to be. There are two special vectors that you might see once in a while. Well, one is called the zero vector, and we're going to write it like this, zero vector. And this is a vector whose magnitude is 0. So we don't really see it. It's so small, we don't really see it as zero vector. There's another one that we might see also that's called a unit vector. And this one is a vector whose magnitude is 1. So if they're talking, they're presenting a vector and they're telling you this is a unit vector, you need to realize that the magnitude is 1. After the length of your vector, you're going to need to think about the direction of your vector. So the direction of your vector is the angle formed by your vector, so by the vector, and the horizontal line. That's passing through its tail. So passing through its tail. So for example, if you have a vector, certain vector v like this, we need to find the horizontal from the tail, and that's the angle here. You realize that, very important, we're always measuring counterclockwise. So this is measured counterclockwise. Okay, so we always go that way. On a Cartesian plane, you're going to have to find the horizontal component and the vertical component. So I'm going to show the horizontal component in green. So if I start from here and I'm going horizontal, I'm going this way. So this will be my horizontal component. So I'm moving 4 in the negative plus 3 in the positive. So I'm moving 7. And the vertical component, I'll put it in blue. When I'm here, I'm going down 3, so this will be my vertical component. So when you write your vector AB, you can say AB is equal to 7 horizontal and 3 vertical, -3. Now, if you want to do this using the x and y component, let's say this here is your x1, this is your x2, and this is your y1, this is your y2. So if you're looking for just the algebraic way of doing it, you can write this, ABX, which means the x component of AB. It would be 3 minus 4. Oops, which is equal to 7. If you're doing the AB component x, y, then you start with your -1, -2, which is -3. So you have two options to find your solution. Look on the graph and draw, or you can use your coordinates. Now, if they're just giving you the vector, but they want you to find the magnitude and the direction. So the magnitude, I'm going to put it in green, so we're looking for this. How long is your vector? And the direction is our angle with the horizontal here. Okay, so what you can do is you can complete your triangle with your horizontal component and your vertical component. So this one here, I have 1, 2, 3, 4, 5. I have 5 here. 1, 2, 3, 4, 5, 6, 7, 8, 9, and I have 9 here. So if you want, if you remember how we are looking for angle, in front here, this is my opposite side, and here, this is my adjacent side. So I'm going to use sine, cosine, or tangent. You can remember your SOHCAHTOA, right? Sinus is opposite over hypotenuse. Cosinus is sorry, and then TOA. So adjacent over hypotenuse, and we have opposite over adjacent, so we're going to need tangent. So tangent of our angle is opposite over adjacent. Now, how do we figure out our angle? We do tangent -1 of 9 over 5. Now you take your calculator. They ask you to round to the nearest unit. So you get approximately 60.95. So that's going to round to 61 degrees. Now to find the direction, you can see we have the Pythagorean theorem that we can use. So if you want to find the norm of AB, you're going to do a squared plus b squared and then square root. So square root of 5 squared plus 9 squared, which is equal to square root of 106, which is about 10.3. So what you can do when you write your final answer, you can write AB is defined by 10.3 units at 61 degrees. So you realize that we can represent vectors different ways. So for example, in Word, you can say, I can walk 2 kilometers, 45 degrees south of east. What does that mean? So if you remember north, south, east, west, if you're south of east, okay, so you're 45 degrees here south of east, and you're going 2 kilometers. So that would look like this. In a graph, it would look like this. Or we can say, oh, we're using components. So for example, 2, 5 is my vector v. So if you want to see what it looks like, you start here, you go 2. So 1, 2, 1, 2, 3, 4, 5. So this is vector 2, 5, and you can place it where you want in the plane. It doesn't have to start from 0, 0, right? Because see my picture here, I can move it around. It doesn't have to be at 0, 0. It's still the same vector. All right. So what if you have, for example, in this one, to find A and B? How would you find that? So I suggest that you pause, try to figure it out, and then come back to find the solution. Okay? So so first we have 220. We know this part is 180, right? So if we take 220 minus 180, we get 40 degrees. So we know that this little part here is 40 degrees. If I'm looking for this one, which is my opposite, and I have here my hypotenuse, so what should I use if I have opposite and hypotenuse? I can use sine of 40 is opposite over hypotenuse. And then how do I find my b? 6 sine of 40. If you type on your calculator sin sine of 40, you're going to find that b is approximately 3.85. So which answer do you think is best? Okay, we're going to keep the answer that's more precise. If you want to find A is adjacent. So if we want to find adjacent, we're going to use cosine of 40. It's going to be A over 6. So A is 6 cosine of 40. Also, if you try this on your calculator, you realize you're not going to get a precise answer, right? So what's more important to keep is your precise value. So when you want to define vector AB, you can say that AB is equal to the x component is, now because it's going backward, you need to think about the fact that it's going to be negative. If you look on the picture, your A is going backward, right? So when you write it as a component, you have to think that it's going backward like this. So it has to be negative. And when you do your B component, it's going down also. So your B component has to be negative also. It's going to be minus 6 cosine of 40. So this you're going to have to think about when you adjust your component. Now when you're going to have more than one vector, there's few vocabulary words you need to know. So 4 that we're going to review together. Equipolant mean that they have the same length, same direction. So that's pretty easy. Same length, same direction. They can be anywhere in the plane, but they have to be the same. Okay, so for example, if I'm taking this one here and I move it around, it's still going to be equipolant. It can be anywhere in the plane. Okay, opposite, they're going to have the same norm or same length, so same norm, but they're going to have opposite direction. So what does it look like? So I'm going to take this one here, but the other one has to be same length, but opposite direction. So it's going to look like this. To be collinear, they need to be in the same line. So for example, this one, and I'm going to put it red, this one. So do you see? So they have the same direction, but they can have different length. So what's important to remember is the same direction. And the last one is orthogonal. That means that they are perpendicular. Perpendicular. So this is going to look like, remember perpendicular means 90 degrees. Okay, so if I have one that's like this, the other one has to be like this. Do they have to cross exactly like that? No, not necessarily, but if I move them around, I will see that they are 90 degrees. And finally, the last topic is the projection of a vector. So the projection of a vector AB, so if I have a vector AB here, on the line C, I'm going to call the line C here, is passing through A, so it's going to start from here, but it's going to go to B prime. And what is B prime? Is when you take your B, imagine that you're coming down at 90 degrees. This is going to be my B prime. And so the projection is going from here to here. So sometimes I use the example of a flashlight. Imagine that I have a flashlight up here that projects light. Imagine that the light is coming down here. It's going to project a shadow of the blue projection. So this is what we call the projection of a vector. It's what's in blue. So if you look at the different diagrams here, the first thing when you have a vector AB is you take your B, you have to come down at 90 degree. Sorry, let me try again. So imagine you come down at 90 degree. This one is going to be very short, very small. I'm coming down at 90 degree, and then I go from the tail to this part here. So this is my projection. Look at this one here. AB, I'm starting from B, I'm coming down at 90 degree. And then I start from my A and I project this way. And the last one is special because if I project at 90 degree, I come down here, right? So the last one, the projection is, if you talk about AB prime, because your prime is exactly on that, this is the zero vector because the line is already perpendicular.